right, what I wanted to talk about now is the notion of convergence. And really, this is in particular with respect to finite element analysis. Okay. So convergence is a much more general concept. It has to do with basically as you refine your numerical method, how quickly does the error go to zero? All right. So let's talk a little bit about that. So we know. Let's do an example. And I think this shows it the easiest way. Let's consider. Well, let's consider our good friend the constant strain triangle. For the constant strain triangle, we know that it's linearly complete in the displacement. So the displacement, I'm going to put a superscript S to denote that this is an approximation. This is the FEA interpolation, okay? And usually it's a function of H, where H is kind of thought to be related to the element size. So H refers to the size of the element. As H gets smaller, your error should get smaller, all right? So for a constant strain triangle, this is going to be contained in the space of linear polynomials. So that means it's something like beta 1 plus beta 2x plus beta 3y. That's our interpolation. So if you think about it, you could have any type of displacement field. So the actual displacement, we can think of it as the finite element interpolation plus higher order terms that are dropped in the interpolation. So for a constant strain triangle, what are we missing here? We're missing things that are quadratic and higher. So we usually write that as h squared. So this means, this is what we call O notation. This means all the terms that are h squared and higher. These are the higher order terms. And instead of using x or y, we talk about h because basically, even if there's some dependency on x with regard to the element size. As the element size gets smaller, right, the x interpolation ability gets smaller. Right? So the displacement error, the error in U, is actually equal to the actual displacement minus the approximation. And you can see that's just going to give me terms that are on the order of h squared. So the error in the displacement, we can write that as something like some constant times h squared. Now if I take the log of both sides, usually it's the natural log. Actually, technically it should be the base 2 log, but now if you take the log of the right-hand side, this is the log of this product, that becomes the log of c plus 2 times the log of h. So now if we look at this, we've got the equation of a line where this is y. I'm going to call this x. This is the slope, m, and this is the dc offset b. So if I were to plot the log of h and then the log of the error on the y-axis, what I would expect to see is a straight line with a slope of 2. Okay? So this is a little weird to look at, except we like to look at convergence in terms of a line. If one were to actually plot initially one might be interested in seeing the error versus the element size. And what you'll see here is that you get curves that look like this. All right? As the element size gets smaller, the error is going to drop down. Okay? Now, what we like to associate with a better approximation are ones that the error drops more quickly. Let's see if I can find another color. I think that's all I got. Oh, here's red. Okay, so we'll get a red with 2. So you can see those have better convergence. The error comes down more quickly as h decreases. Now likewise, when we look at it in terms of the log-log plot, you tend to get linear results, lines I should say. So we tend to see results like this, okay? For example, this is second order, all right? You might have other ones where the slope is like 3. So this is better. That is better convergence, okay? And you can see that easily too. If something has a convergence that's cubic versus quadratic, let's just look at the error real quickly in a table. Now let me put it on another plot. Do it over here. Let's look at h. And then we'll put the error for something that's h squared. Well, I should say. And then the error for something that goes as h cubed, okay? So let's first put off h as 1. Okay, and then, if h squared is equal to h cubed, they're both about the order of 1. Now if I take the element size, so this, let's say, corresponds to an element like this, and now we half the element size. So h has gone to a half, all right? This becomes a quarter, and this becomes an eighth. So already the error started to drop more quickly with the cubic convergence than the quadratic convergence. And now if we take the element size again and halve it, this becomes 1/4. This becomes 1/16, and 4 to the third is 16. 4. What the heck is that? 16 times 4 is. Boy, I think I would know these things, right? It's 24, 2, 4, 5, 6, 16. That's 4, 2. 224, is that right? Wait, what am I doing? Yeah, I guess that's right. It's 224, 1, 224. So you can see how quickly the error drops off when you have things that are one order higher in convergence. So this type of convergence we call second order convergence. This would have third order convergence. You could have fourth order, or likewise you could even have first order convergence where the error goes directly as h. So if you had first order, your error would actually go just as h does. You have the element size, your error drops in half. So if you can get higher order convergence, your errors drop off very quickly, okay? So even if you compare similar amounts of degrees of freedom, like for example, here's the error. Well, yeah, you just tend to get better performance, okay? Now let's go back to the results we did up here. So for the constant strain triangle, you can see that we get second order convergence in the displacement. All right. Now, what about the stress? Let's look at the stress. Well, the stress is proportional to the strain. So let's look at the error just in the strain, right? The strain is basically the derivative of the displacement field. So if the approximation of the strain for a constant strain triangle is going to be, I'm sorry, let's do it this way. The strain is the approximation. The truncation error is going to be the derivative of this, or it's going to be order h, right? And we kind of know that this is, these are constant terms. It's a constant strain triangle, so the strain is constant. And then the higher order term, the next one would be a linear, okay, constant, all right? Now in this case, you can do the same thing. The error for the strain is basically equal to some constant h to the first. And then if we take the log of both sides, you see we get. All right, so this would have a convergence rate of 1. So you can see it's the same element, but you exhibit higher convergence for displacement than you do for strain. And let's assume that the error in the strain is nominally equal to the error in the stress. The stress will converge in the same way. This is true for all elements. So the convergence in displacement will always be, well, there are some weird multi-field elements where you can actually improve on this. It will always be one order higher than the convergence in the stress or strain. All right? So that means if you are interested in displacement results, you don't need as fine as the mesh as if you're interested in stress and strain results. Okay? So when we do modal types of tests, where you're just worried about the deflection of plates, you can get away with a much coarser mesh than if I'm worried about, you know, maybe the stress concentrations that happen around some feature. Right there, we really need to zone in on the mesh or something, right? To have a refined mesh, okay? Okay? Now, what happens when we consider a higher order element? So, for example, let's consider the linear strain triangle, okay? So this is the linear strain triangle. All right. So in this case, the displacement error is going to be one order error than its approximation. So we know the approximation here is going to be stuff it's going to be on order of h squared. It's complete to a quadratic polynomial. So a linear strain triangle can exactly represent a quadratic displacement field. So the truncation error here is going to be the next higher term. So it's going to be order h cubed. All right. So again, if we take the log of both sides, well, this is ch to the third, right? So we'll get ln of c plus 3 ln of h. So here's the convergence rate. It's third order, okay? So it's going to exhibit third order convergence. So it's okay. Now, the stress result is going to be one order less than that. So it's going to be second order in stress, okay? And you can see from what we had before, from these, how dramatic a difference you can get. So The linear strain triangle and displacement is here, and it's here with regards to stress. The constant strain triangle is here with respect to displacement, as opposed to here, and it's here with respect to stress. So you can see how you converge much better with the higher order elements. So, you know, basically, if you have an element that is an nth order complete polynomial in the field that approximates, in U, right? So for example, this is quadratically complete. Then this becomes order n plus 1, convergence in the displacement, and order n, convergence in the stress. So basically, whatever the order of the polynomial for the interpolation is, that's going to be the convergence in stress, and the displacement convergence will be one order higher. So, right, constant strain triangle is linear. It's a linearly complete approximation for U. So that's n is equal to 1. So here, the convergence in U is going to be 2, and the convergence in stress is going to be 1, or first order. All right. So if you had the next highest order element, which is the cubic element, this is cubically complete, so n is equal to 3. So that means that it's going to be fourth order in the displacement and third order in the stress convergence. Okay? Now stuff like the the bilinears, they fall somewhere in between. So what you'll see here is something, although this is linearly complete, but it has a little bit of extra term. So it'll actually do a little better. You know, n is like 1.5 maybe, right? It's linear, but remember, it also has the xy term. So it's not fully complete quadratically, so it won't give you n of 2, right? It's going to be n like 1.5. So that means the convergence in U is going to be like 2.5, and the convergence in the stress is going to be about 1.5. All right? All right. Let me mention one other. So sometimes, so that's how you can theoretically estimate the convergence for your finite element mesh. Sometimes you have other reasons, maybe some new methods, or you have other things like contact, and you want to know the convergence. Well, you can always do a sort of a numerical test of convergence. All right? So if you have some problem and you know an exact solution, let's say we have like a beam problem, and I know what the actual deflection is, right? So then I can start off with one element, right? This would be, let's say this is about h equal to 1. And then we can get the delta for h equal to 1. And then we can compute that error, okay? And then we can take the mesh and refine it. That would be h equal to 1/2. And then we can get the delta at h equal to 1/2. And then the error, so on and so forth. And you can keep dividing elements, right? And then you can actually make the plot, the log of the error versus the log of the element size, and you can then get the slope. So you actually would plot discrete data points. You could actually get the slope. So that slope is your convergence. All right? So if you plot the error and displacement, that's going to give you the convergence and displacement. Now your convergence and stress will most likely be one order less than that, so you can subtract 1. Or if you have a result where you know a stress, you can plot the convergence for stress, and your displacement convergence will probably be one order higher than that. So you can actually numerically test the convergence. You can actually also do this if you don't have an exact solution. And this gets into this concept of a Richardson extrapolation, and it can give you a guesstimate on your MECH error. And I think actually I'll talk about that later. So in the homeworks, when I ask you to check the convergence, this is what I'm asking you to do. And you should be able to check that the convergence you get experimentally through the finite element results matches the theoretical ones. Okay? Okay, that's it. Let's stop there.